working on. And
Okay.
no, this is just give a couple of minutes
Yes, yeah.
just to be in due
So,
time.
yeah.
I think we have about 2 minutes to go.
Yeah. So it is
Because
scrolling also, right?
yes, it's very, very
Yes.
well.
Okay.
I can see alpha and beta and so on.
Yes. Yeah, okay.
Which is more than enough. And some kids.
Yes.
The other day I was thinking about Paul Dirac
Hmm.
and his lovely book he wrote.
Yes.
Do you have a copy of that book?
No, I do not have any copy of that book, but you can share if you have that book with me.
Yes, and this is what I'm going to do. I'm going to share that for you.
Yes. Yeah.
And it's a lovely book. It's one of the very best I have ever read in my life. You will see how happy you will feel by going through pages and pages and some equation. That you know the importance in it, that the way that he looks into physics. It's very nice. I'm going to share it as soon as I can to your email, okay? Well, so far we have Marco Alfaro. He's a very good friend of mine from Chile. We have another gentleman, Galaxy A71, which I think he must be from India, I think.
Yeah.
And I do welcome everybody to this talk.
Yes.
Well, I would like to introduce you. In this opportunity, Professor Debabrata Datta, a senior scientist from ahead biological physics and advisory at the divisions Atomic Research Center, Mumbai, yes, Joint Research Director, Heritage Institute of Technology, Kolkata. Now, he's a professor. I would like to thank you once again for your kindness and friendship all along many, many years so far. Professor Debabrata Datta is going to talk about quantum computing to develop quantum finite difference solver, which is a very nice subject. And I hope that everybody is going to enjoy this. We are recording this, and this is going to be in YouTube and in places like LinkedIn and so on. So people will be more than welcome to look at it. And once again, Professor, thank you very much indeed. And we will appreciate your effort and energy to teach people and to let people know about so many different areas where you are an expert. Well, I have a small set of words to say about Professor Debabrata Datta. Nevertheless, his curriculum vitae is brilliant. He's an outstanding scientist. And I would like to acknowledge him and all the Indian people because today they celebrate the Independence Day, which is a very important date for everybody all over the world. My dear professor, you are more than welcome and you can start, please.
Okay. Thank you very much for introductions. Nice introduction about me. And I think prior to this lecture also, several times I came on the screen along with Professor Roberto, and my all the sincere thanks to him for arranging this kind of webinar, for connecting the two cities which are quite far apart, and we can see that the technology reduce the gap between these two standard locations. Well, today's topic, as he has mentioned, that I will be describing about the quantum computing to develop a quantum finite difference solver. Okay, so there are many things to say about the quantum computing, because as we know that day by day we are approaching to this quantum computer where we need quantum programming, which is totally different from today's programming angle. Okay. So my presentation from that angle, I have just kept into these slots. I will be describing about some preliminaries about the qubits, because this is the basis of the quantum computing. Then with the help of the qubits, we will discuss about something of quantum gates. And then from the quantum gates, we will switch up to the quantum circuits. And these quantum circuits will function on the basis of some quantum algorithms. And then quantum algorithms, one of the algorithms which you can use for designing this actual topic of these presentations, that is quantum finite difference solver. Then we will finally conclude that, and we will see that there are many things can be done by using that particular algorithm. Of course, everything will be on the designer's choice and developer's motivation. Okay, from that angle, let us discuss about the preliminaries of the quantum bits. If you look at classical computer is based on the 0 and 1, that is true or false, and these two are together called as a binary digit or bit. Similarly, in quantum computation, a bit is replaced by quantum bit, and that is the short form of this is the qubit, which is in state 0, and that will be represented as this kind of vector, and we call this as a Dirac notation. Similarly, a qubit in the state of 1 is represented as state 1, and this is also a Dirac notation. So, first stage is that the quantum computing, that we are talking about the 0 and 1, but these 0 and 1 are not the only values, they are basically states. So 0 state will be as represented by this, and qubit state 1 will be represented as this. And their matrix formation or matrix representation will be nothing but that. So we can say that quantum bit 0 and quantum bit 1, they are basically column vectors. So qubit states are the states in which we determine the measurement of the qubit. So you are interested to know that what is the probability of the state in this particular state or in this state. So therefore, many of the time, a qubit states we determine with respect to a z-axis, and this state 0 that will represent as a z, and this z will be having some kind of basis. And if we represent the x and y component of these two bases, we can have this preliminary concept of qubit as a superposition concept of this. If you see that this is one particular state which is formed by a superposition of the state 0 and state 1 with a normalizing factors of 1 by root 2. Same way, if we take this state, which is superposition of these two qubits with a normalization constant of 1 by root 2, and so on. So that means in the case of quantum bit, it is possible to have a superposition concept of these two bits. And because of the superpositions, the quantum computation is normally faster than classical computation, speed-wise. Okay, now how fast it is, that will be judging in the due course of this presentation. Well, if we look at the sphere, so this sphere to represent the a quantum state 0 and quantum state 1 is nothing but the two poles, you can say, and this space is called as a Bloch sphere. And we have seen these are the nothing but the pole states, which is represented by this expression, and also this particular x component is represented by this expression. So we can say that we have a linear superposition of these two bits with an coefficient as alpha and beta, and they're basically complex numbers. If we physically look at from the photons angle, this will represent not only linear polarization, but also it will represent that the circular as well as elliptical polarization. Okay. So we can say that if we try to measure the qubit, then the state 0 or state 1 will be measured with respect to their corresponding probabilities, that is mod of alpha square or mod of beta square, and then the system will be left in the state of this or this. So this is the visual representation of these two particular states. So we can say that as a simple proof that there is a 50-50 chance of being the state either in this form or in this state. And this is proof is here basically. You can see that the 1 by 2, and that means 50-50 chance is giving from the superposition principle of these two states. Okay. So if you look at the example, so suppose this is my linear combination with these two states. So if we introduce some orthonormal basis, this is my orthonormal basis vector. So I can write down that the probability of being in this state is nothing but alpha plus beta of mod squared by 2. And similarly, probability of being in the state will be representing by this 2. So it is very simple to introduce some kind of orthonormal basis, because in quantum mechanics, the particularly we require to know that the basis vectors in detail. Okay. So with the help of simply preliminary qubit concept, we can design several kind of gate, which is nothing but the quantum logic, we can say. So these quantum gates are very, very important to understand the quantum logic gate. Okay. Some people call quantum gates, some people call they are the quantum logic gate. So they are similar to the classical gates, but definitely they do not have a degenerate output. That means their original input state can be derived from their output state uniquely. And the very different from the classical gates is that classical gates are not reversible, means from the output you cannot go back to the input, but in the case of the quantum gates, from the output you can go back to the from where they have come. So they are basically called reversible. So quantum gates has to be reversible. Because of the reversibility conditions, automatically some kind of transformation we require to design for doing these functions. Okay. So therefore, what is the meaning of the quantum gates are reversible? That means we can have a deterministic computation that can be performed on a quantum computer only if it is reversible. And because of this, you can see that this Charles Bennett in 1973 has given this deterministic computation, and he has shown that this can be made reversible. This following his work, we understand that the reversible computation is very much essential in case of the quantum computation, and that is only achieved by the quantum gate. So the main point of introducing quantum gates are there. With the help of the quantum gate, we can do the quantum logic, and these quantum gates are basically reversible. Now, if you compare some classical gates, and then we can see that in classically we have various kinds of gate which follows a Boolean algebra. In case of the quantum gate also, the truth table follows a Boolean algebra, or we can say that a control knot which is given into this. This is the control bit and this is the carry bit. So therefore, you have some kind of operation where the truth table is designed as a matrix. Okay. And here we have seen that every classical counterpart has a quantum counterpart. If we have a NOT gate, we have a quantum NOT. This is a quantum classical AND gate. So we have a quantum AND gate. This is an exclusively OR gate. We can have a quantum exclusively OR gate. This is the OR gate. And finally, we can have the NAND and NOR also. Okay. Now we are explaining the one by one, because before going to the final topic, we have to understand the quantum gate, then quantum algorithm. And since the gates are fundamentally built on the quantum state, so that is why first couple of slides I explained that what is quantum bit. Now, if you consider that the single qubit gate, you will see that qubits represented by 2D vectors and their states are given in the form of this. Okay, so that means state Q is represented as a cos of theta by 2 and ket 0 plus e to the power I phi into sine theta by 2 of ket 1. So this means it is also encompassing a phase transformation because the phase is involved here. Okay, so the list of gates are like that. We have a Pauli gates which are XY design a quantum gate in the quantum mechanics. Okay, so in the Pauli X gate is matrix form representation is nothing but this one. Okay, that we know from the Pauli spin operator. So operators is nothing but a matrix representation. And that is why Pauli X gate is represented in the form of a matrix like this. Pauli Y is a Y gate is represented by Pauli spin Y, that is sigma Y, and Pauli Z is nothing but a sigma Z, which is a Z gate, and matrix representation of this form. So therefore, we can easily say that X gate. Now the question is that what are the implications of these three gates? One of the implication is that every gate will be representing some kind of thing. What is that? If we try to understand that the NOT gate, which is classically we know that if we send a 0 bit, we will get the output as a 1 bit. Okay. Similarly, if you look at the X gate, which is a NOT gate, in quantum computation, X gate is a NOT gate and Z gate leaves ket 0 unchanged and flips the sign of ket 1. Let us see a simple example. Suppose I am operating the Z gate on the state of psi. So psi is nothing but the alpha and beta. So Z is obviously alpha and beta. As the Z matrix representation is given as a 1, 0 and 0 minus 1, you simply do a matrix multiplication. You will get the alpha minus beta. Now this alpha and minus beta I can write in the form of a single line, which is the alpha of ket 0 minus beta of ket 1. And as I mentioned that it leaves 0 unchanged, but flips the sign of minus 1. So that is the minus k. So that is why we can say that Z gate behave like this, whereas X gate is nothing but the NOT gate. We will explain what is the function of the Y gate. So now we can say that the X gate is represented by the Pauli X matrix is nothing but that, which can be written in the form of that. Okay, and as we know that they are just entangled. Okay, so this kind of multiplication is known as the entanglement in the field of the quantum computing. So therefore, we can say that the effect of this gate has on a qubit. If I operate the X gate with the ket 0, you will see that the X is represented in this form matrix and ket 0 I am multiplying. Ket 0 is nothing but the matrix form of this, vector form of this. So if you simply multiply, you will get the 0, 1, which is nothing but the 1. So therefore, we can say that the X gate, when operating on the ket 0, it gives the 1. So that means it is a NOT gate, which I had mentioned previous slide. Similarly, Y gate is this and Z gate is this. So if I operate the Y on this particular, this one, that 0. So by using the matrix multiplication, you will get that the Y is nothing but that. So therefore, it is giving a complex transformation, whereas Z, we have explained that ket 0 remains unchanged, but ket 1, it's changed the sign. So flip the sign. So in the block sphere, we can say that they are basically representing a rotations by pi around the y and z axis of the block sphere. Okay. So we can say that with the help of the x, y, and z, because the Pauli gates are basically termed as a basis space in the quantum computation. And therefore, the computational basis can be done. That means I can design some more gate with the help of this Pauli gate. And this representation, we can say that a popular basis, the X basis, formed is an eigenstate of the X gate and can be mathematically represented by these two vectors. Okay. Coming back to the next set of gate is known as the Hadamard gate. Okay. And this gate is also known as a square root of NOT gate. Now you see, we call that the Hadamard gate because of the Hadamard matrix representation is nothing but that. But when you do the performations, then you will see it is also behaving as a function of the square root of a NOT gate, which is not available in the classical computation. Classical computation, we have only NOT gate, but we cannot do any kind of performation of the square root. So therefore, obviously, if we design the hardware, we can get the square root operation directly by using the NOT gate design. So this is my Hadamard gate. And if I operate the Hadamard gate, suppose the state 0, you are operating on the Hadamard gate, you will get the state 0 plus 1 as a linear combination. And then again, if we send back to the another Hadamard gate, you will get the state 1. So what does it mean? That means that the two Hadamard gate directly in series, if I operate, then Ket 0 is reflected into the Ket 1. So that means these two behave as a NOT gate. Okay. So we can say that the two Hadamard gates used in succession can be used as a NOT gate. There can be many more design can be done, and those who are interested, they can do a they can play around some kind of combination of Hadamard gate, which will give some kind of other gate like this. Okay. So you can see that the detailed example, this is my Hadamard gate representation in the form of a matrix. So if I operate this two, that means this is the state which is taken as a alpha of Ket 0 plus beta of Ket 1. If I operate on that, I'll obviously, by its matrix multiplication, I can write down the algebra into this form. And therefore, if we do that, you can see that the alpha beta will be represented as this form. So alpha will be there. So therefore, we can write. So this is the proof of that. The matrix H can be used, that is Hadamard gate representation can be used to know that how it can operate on a general qubit. Okay. So we can say that the one input gate, any gate can be single input, can be two input, like that only we can design the quantum gate. So therefore 1 by root 2, 1 by this is my Hadamard gate. And if we try to do that thing, we have got this already. And if we ignore the normalization factor, we can write this form as a classically states can be represented as a minus 1 to the power x of Ket x minus of 1 minus x. I am leaving the proof to the reader or the participants who can prove that any kind of classical state, ignoring the normalization factor 1 by root 2, we can write into this form. And this is the design is possible only. And with the help of the design, we can do some more operation of the quantum gate. Okay, let us some kind of digression occurs. We can write that a general probability on this is nothing but this one. If we do the mathematical operation, we can get it, that I have skipped here. And P of operating on the decade state, obviously, this probability. Okay. When you do this kind of thing as a square, it is representing as a probability because this is a measured state. Okay. So therefore, as a digression, we can say that after some kind of measurement, the main point to be noted that the superposition is destroyed. Okay. So you can create an X gate by sandwiching our Z gate between two H gates. So if you look at I am designing an X gate, and this X gate, how do I design by Hadamard gate? I am just sandwiching a Z gate by these two Hadamard gate. Okay. And if you do the matrix operation, you will obviously get that. So H is nothing but my 1 by root 2 of 1, 1 minus 1, 1. And Z is nothing but my this matrix. H is again that. So if we do simply a matrix multiplication, the result will be coming as a 0, 0, 1, 1, which is nothing but my Z gate. Okay. X gate. So therefore, an X gate can be designed by these two operation, that is the sandwiching the Z gate between two edge gate. Okay, so this way a circuit can be alternately given for designing some kind of gate. Okay. Now coming back to the T gate. T gate is basically called phase gate. That means a phase transformation occurs and its matrix representation is nothing but this one. That the P of phi is a 1, 0 and 0 of e to the power I phi, where phi is basically a real number and it gives some kind of rotation of the phi around the z axis. So when there is a rotation needed, we can use the T gate. Okay. Next set of gates are the I and S gates. I is, as already mentioned, which is an identity gate, and its matrix representation is this. And we can write I as a XX, where X represents the Pauli X gate. That means 2 Pauli X gate. If we simply multiply, you will get the identity gate. This is required for only designing for the hardware of the quantum computer. And also that the logic will be built, and based on that logic, we can design some kind of mathematical operations or physical operation. So we can say that applying the identity gate anywhere in your circuit should have no effect on the qubit state. So it's interesting. This is even considered as a gate. Okay. Next set of gate is the S gate. S gate sometimes known as the square root of Z gate. And this is also a P gate with phi equal to pi by 2. So matrix representation of the S gate is 1, 0, 0 e to the power I pi by 2. And obviously, in quantum mechanics, everything should have some adjoint, and this adjoint is called the dagger. So this S dagger will be 1, 0, 0 into the power minus I pi by 2. And if we know that the S dagger S is equal to identity, then this S matrix or S gate is a Hermitian gate. So therefore, all these matrix in this quantum computation is somehow either you call magically or by pure mathematically is known as a gate. So we can write that the SS2S gate, we are operating on the Q and we are getting the ZQ. So I can simply say that when the state remain unchanged, so eigenvalues of the 2 SS2S gates in a multiplied form is nothing but a Z gate. So I can explain that what is the Z gate? Z gate is nothing but an eigenvalue of the 2S gate. So therefore, simple S gate would be square root of Z. So that is why we mentioned S gate is sometimes known as the square root of Z gate. Next is the T gate. T gate is very commonly used gate, which is an T gate with a phase equal to pi by 4. And we can write that the matrix representation 1, 0, 0 to the power I pi by 4. So therefore, obviously, T dagger we can write 1, 0, 0 e to the power minus I pi by 4. So therefore, as with the S gate, T gate is sometimes known as a Z to the power 1 by 4 gate. So various power of Z gate can be designed by using this two combination of the S and T gate. So this is a simple operation that how we can do by the S gate and all these things that we have already explained. But one thing we have to know that the matrix U, which will describe the qubit gate, that has to be unitary. And unitary means that the U dagger of U should be equal to I. Okay. So if you look at the phase gate as this, so therefore you operate on that, what will be the result? I have just shown that a simple mathematics from here. S of 1, 0 will be giving 1, 0 because shift remain unchanged. It leaves state 0 unchanged. But when you go for the another one, that is state 1, so you will see that it has got changed and the phase. Okay, that the shifting has been taken place. Similarly, pi gate is, I explained, pi gate is pi by T gate is nothing but that. Sometimes it's called the pi by 8 gate because a phase of this pi by 8 is already introduced while doing some operation on that particular state. Okay, this has been explained into this form. So using this, we can explain some kind of rotation operator because Pauli matrices X, Y, and Z that gives the rotation operator. So these rotation operators, as usual in the classical sense, we can design by this kind of matrix representation, and we can do any operation if it is required some rotation. Coming back to the qubit states, we can have the multiple qubit states also. And when you have the multiple qubit state, then they get like NAND or NOR can be designed. And here is an example of the control NOT, which is a C NOT. Since the control NOT, we call it the control NOT. And you can see that if both the multiple gates means 2 qubits are there. So if the 2 qubits are both 0, it will remain that the 2 qubits 0. If it is 0, 1, it will be remain as a 0, 1. But if it is a 1, 0, then it will be changed into 1, 1. But if it is a 1, 1, then it will be changed into 1, 0. So therefore, one bit is controlled by this gate. That is what is called control NOT. And first argument is called the control, and the second one is called the target. So that is the design of the control NOT gate. And this is the design basically. First qubit is say gate A, which will remain unchanged. But second one, it will change into a prime. So that is why if I do this truth table AB and AB prime, you see that whatever I mentioned, it is coming in here. So we can say that control qubit 1 is flip the target qubit. Okay, so that is the basic idea of that. So if you write that the U00, you will get the U0. If you write 01, you will get this one. If you get U of 10, you will get 11. If you get U of 11, you will get 10. This is the operation generally I am explaining. So 2 input gate, we can call that the control NOT. So in the control NOT, I have a X state, another is a Y state, that is a qubit of X and Y qubit. X will remain changed, but when you go for the Y, it will be given as a exclusive OR operation of this one. So this is the difference of between the classical NOT operation and quantum NOT operation. Okay, this is the control NOT. So therefore, you can say that the C naught maps into this, and C naught of XY will be XZ, and you can substitute that the X, the 0, 1, 0, 0, you will see that this one. So Z is nothing but your X exclusive OR of the Y. So simply X naught Y, if you give C naught X and Y, you can see that the X has remained X, and Y will be remain at the X exclusive OR of Y. So these operations are to be remembered, because when you go for the programming, so these operations are to be carried forward, means it has to be carried out with respect to some language. So C naught can be used to produce an entangled state, as I mentioned already, and C naught of X0 is giving, which is a fan out logic, and C naught of 1 is giving. So fan out and fan in, these two logics are available in the electronics. Many kind of polarization concept has to be designed with respect to fan out logic and fan in logic. Okay. So we can have a multiple qubit system. Now you see, I have a multiple qubit system. We can do the measurement, and measurement is always a probability, and general structure of the n qubits can be represented in this form, and this will be representing in the space, which will be called as Hilbert space. And in the, because we know that the quantum mechanics is valid only in this space, which is called Hilbert space. So Hilbert space is a very big place, and there we can design many of the things. Remaining things are all story, and which is given by U. Manning in 1980. We can have 3 input quantum gates. 3 input gate, say control NOT. That means C square NOT. C square NOT, you see, sometimes it is called the Toffoli gate. Whatever the Toffoli gate we have seen, that T gate we have seen. So designing some T gate, we can do the C square NOT. So the Toffoli gate, the truth table can be designed in this form of that. So since they are controlled, so it will remain same. But if it is not controlled, then automatically, because of this sign, the C will be replaced by AB, exclusive operator C. So therefore, we can say that the C square NOT is a Toffoli gate, and Toffoli gate can be alternatively called as a NAND gate, and also Toffoli gate can be used to make a copy of certain observation. Okay. So this is the A NAND B. You see that the A is controlled as A, B is controlled as 1, and if I give that the 1 bit, then definitely A NAND B operation I will get. So therefore, C square NOT will be a NAND gate, and remaining things are obvious. You can do that as a homework with respect to that, the various change of the C square NOT gate. Okay. Finally, we have a discrete universal gate set, which is a 4-member standard gate set. So that means I have a Hadamard gate. This is my control NOT gate. Hadamard gate, phase gate, and pi by 8 gate, which is the T gate. Okay. So C naught, Hadamard, phase, and Toffoli. So these four can be a basis, or with the help of that, we can design many kind of gates. Okay. Sometimes we require to have some kind of transformation, and this transformation is known as the Walsh-Hadamard transformation. And Walsh-Hadamard transformation is defined into this form, which I have shown. This is nothing but the H of operating on 0, and this one is nothing but the H operating on the ket 1. So I can take a linear combination to get this kind of thing. So this type of transformation is very, very important to do a structure called quantum key distribution, and quantum cryptography is based on these two particular things, which is always people explained by this Alice and Bob, because they wanted to exchange the information between these two, but other people present in that, they will not know what they are doing. So that is why cryptographic transformation by using their quantum concept. So therefore, quantum key distribution, which is very important for quantum cryptography, and that can be done by the Walsh-Hadamard transformation. Let us just go through how the gates act on the qubits in a very quick. And qubits can be written in terms of the oscillator states, because a quantum harmonic oscillator can be designed by using the qubits concept. So if you look at this first expression, P gate and S gate, both simultaneously together operating on X, you will get the output as e to the power Ix phi of X. Hadamard gates, you are operating on these two. I had given this kind of concept in the beginning of the slide, that the general X state can be written into this form. And here you are seeing that it is coming from the Hadamard gate operating on that X. Not X is operating on 1 minus X. If we operate the C naught of XY, that we have shown. So this is the algebraical structure of doing the various kinds of gate operating on some general structure of the qubits. Similarly, if I apply the swap of XY, you will get the YX, because X and Y, they will exchange. You have the Fredkin, XYZ, and you will have this operation. These all algebra are very simple, so I'm not going to the details of that. I'm just doing what is the output, because my purpose of taking the output only. Then if I go for the Toffoli, I will have the XYZ, which can be algebraically done by that. So giving this simple concept, that you can see that there are many ways of designing some kind of circuit which is based on this kind of operation of the gate. I can do the Toffoli and swap together and then find out the algebra. And if you do that, you will be having. But remember one point, when you have the two qubit state, it is nothing but the just entanglement of these two states. Entanglement is nothing but the multiplication, but multiplication is not the normal multiplication. It will be following a tensor operation. Okay. So this is the various kind of oscillator state, not of Q, Hadamard of Q oscillator. It is a Q deformed oscillator, swap of Q, C naught. Because of the oscillators, we can have in the solid state physics called Josephson junction. Josephson junction can be designed in the quantum mechanical concept by using quantum computing by these two concepts of the Hadamard of the Q deformed and Fredkin of Q. There may be another way of designing also, but I'm not going to the Joseph, because the topic is not that they discuss about the Josephson junction. So unitary operators and quantum gates I already mentioned, but one thing to be mentioned that the quantum evolution is always an unitary. So this is coming from the postulate of quantum physics. So if U is a linear transformation, then U dagger, which is called conjugate transpose, can be defined by this kind of transpose. That is W comma UV is nothing but the V comma U dagger of W. And we say that the U is unitary, provided that U dagger should be equal to U inverse. Why it is important? Because this gives the concept of Hermitian matrix, and the Hermitian matrix is very, very essential for solving any kind of classical operation in the domain of the quantum computing. So this is the tensor product of the operators. As I was mentioning, that when you have the multiple qubit state, suppose we have a qubit, say mu, and we have a state, say nu and W, and they are unentangled on these two. Now, if we try to combine them like this, so then it is designed into this way, and this is particular product is known as a tensor product. So I'm giving another example. Suppose I am entangling the A and B with the help of this. So that means this I am entangling. How do I write? A of 0 and B of 0 with an entangled multiplied by A and B, and both are entangled into this. So ultimately, I am giving the a result of A, K1 and B. So therefore, we can see that the entanglement can be splitted into two parts. So we define that this one as a, how do I define in physically? I can define that the A entanglement of B, which is 1 by root 2 of 0, 0 plus 1 by root 2 of 1, 1. That will be 1 by root 2 of, when we go for this one, will be 1 by root 2 of this 1, 1. And if we explain this, then I will get the result as a 1 by root 2 A of K0 entangled with the B1, that is the tensor product, plus A of K1 as a tensor product of B of 1. So that one has to write a quantum program with the help of some kind of tensor product concept. Okay. In general, I can write A as my linear combination of these two. Linear combination means I require to calculate the AIG coefficient, and B is suppose this one. So if I try to do A and B a product, explicit product, so therefore I will be submitting this two, and then if we do the little bit of algebra, I will get this kind of. So this is the explanation of the how a tensor product can be formed into this form. Okay. So when you have a several qubit, you will require to have a multiple qubit. With the help of the qubit, we design a circuit which is called as a quantum circuit. Similar to our classical circuit, electronic circuit, we have a quantum electronic circuit, and here only that the quantum electronics will come into picture. Fine. So we have a quantum circuit in a computational routine that is called coherence you have to do there, and so therefore you can say that the coherent quantum operations on quantum data. Okay. So it is an ordered sequence of quantum gates, measurements, and resets, all of which may be conditioned on and use data from the real-time classical computation. So a set of quantum gates is always to be universal, and if any unitary transformation of the quantum data can be efficiently approximated arbitrarily well as a sequence of quantum. That means a circuit has to be designed in the form of a sequence of quantum gates. That's the basic lesson. So a quantum circuit is a sequence of quantum gates, as I mentioned, which is linked by the wires. So remember, these wires are quantum wires. That means whenever there is a transformation, means signal transformation will be based on the pulse. Okay. And therefore the speed of the operation will be exponentially faster compared to the classical wires. So quantum circuits are collections of quantum gates interconnected by these quantum wires. The circuit has a fixed width. We should know that we have to calculate the width depending on how many layers can be designed, how many qubits operation can be designed, that can be easily formed, and logic design attempts to find the circuit structure. And then finally, quantum logic design is not well developed, but it is in the research state. So this is on a quantum operation, which is called the variational quantum eigensolver. Many times we require this kind of quantum algorithm, I can say. You can see that this part is a quantum. Okay, so that means you are preparing a state and you are giving the linear combination. The whole this concept you are transforming to a classical concept, and the output to you will be classical. So you may have a quantum block, you may have a classical block, then you can have the two quantum operations. So that is the design of the quantum circuit, which will represent a variational quantum eigensolver. Okay. So this is a quantum circuits for half adder. I am not going to the detail. As I mentioned here, this is a half adder. So similar to our binary half adder. So it is what is done. You have to have this summation x1 x exclusive or of the x0, and you carry the x1 x0. And this is the design of the half adder. In the generic design, the matrix formation, I require to have the matrix formation only. So matrix to be given to you, which is designed to be as a half adder, can be programmed by this matrix. And then if you go for with the help of our C square naught and C naught, so half adder can be designed. So in the quantum circuits, a half adder can be designed by a combination of the C square naught, which is a Toffoli gate, along the control naught. And if we do this operation, we will get that this one. So we understand that the half adder can be programmed by a combination of the Toffoli gate and control naught gate. This is exactly a visualization of a quantum circuit. You see, this is a circuit which I was explaining is visualized. That means the program, and this kind of program can be written. And for this time being, we use the QIS-Kit module of the Python, which is QIS-Kit module of the IBM, which is available in the Python. So we can do the quantum circuit object. It is written into this form. You design a quantum circuit, call this function or call this object by passing its argument 3, 3. So that means 3 qubit you are giving. And then circuit.x1, if you get, you will get the 1, 1. Circuit.h is a Hadamard gate. This is the Pauli X gate and range of 3. Circuit.control x, if you get 0, 1, then you measure. So you will get if you run this circuit, then you will get this circuit. So, and then hardware, if it is available, so we can design this particular circuit. Okay. So quantum circuits can be known further from the quantum algorithms, because these are the fundamental. Now, if we really do the circuit for a physical operation, then we require to have a quantum algorithm. So that is why I mentioned that the quantum circuits can be known further from a quantum algorithms. These are the quantum algorithms list, which is a quantum teleportation, quantum Fourier transformation, quantum phase estimation. This is the HHL algorithm, like Harrow, Hasidim, and Lloyd algorithm, very useful algorithm, but can be motivated, means can be modified depending on the application. Quantum random walk search algorithm. Then this side you have the Deuce-Josse algorithm, Bernstein-Razirani algorithm, Simon's algorithm, Shor's algorithm, Grover's algorithm, and also an algorithm like quantum counting, superdense coding, and quantum key distribution. So these sets of quantum algorithms are sufficient to know the beginning of the quantum computation. Okay. I'm just giving a simple example of the binary numbers and quantum states. You can write the quantum state into this form as an just entanglement all this one. X can be a n-bit binary number X. Why you represent? Because those two algorithms can be explained with the help of this. So here you see that a classical concept into a quantum. That means I have a function, and that function, how do I write in the form of a quantum? So therefore, I can write into this form, ket x operating on the ket 0, not operating is entangled. So we can imply that the f of x and some extra data. So this can be turned into a computation like if I do the unitary transformation, that is the unitary gate on this, you will get the x into fx. So this is the purpose for that. This method is not to be discussed right now because so many other things are there, but this much is sufficient to know that. Of course, I have mentioned here method. So if you look at the last point, which is giving the exclusive OR operation of that. Okay, so that means if I try to do that, x of b of exclusive OR operation, I can get that. And this is the quantum circuit corresponding to that. Why I explain that? Because the Toffoli gate, I have seen that the C square NOT gate, and using that I have seen which is a NAND gate, but here we can say that the classical version of AND gate by using this operation. So using the Toffoli gate as a quantum version of the classical AND gate is nothing but this. Okay. Similarly, if we have a different kinds of function, we can have a various kind of type, and the corresponding quantum circuits are represented by this. This is very useful for writing some quantum program. This is the first algorithm, quantum teleportation. Teleportation means a person or object disappear while an exact replica appears, in the best case immediately at some distant location. Okay. So that means two persons are just doing some kind of Alice and Bob, as I mentioned. They are just trying to discuss with them, but they will send a type of algorithm which is known as a quantum teleportation. And with the help of that, the message passing by one fellow to another fellow will be known only between any third person present, they will not be known. So that can be used as a quantum key distribution. So we can say that the application of the quantum teleportation is that in place of writing in a large quantum computer, we can just some cryptographic concept of that. So to build a distributed system that is called quantum multi-computer can be taken care by quantum teleportation to implement that. Okay. And this is the quantum teleportation circuit. See, every algorithm is behaving as a circuit. So ultimately, to achieve that, we have to follow the programming concept into here. And this particular thing, if we understand, see, this programming concept is nothing but the matrix operation of this. So ultimately, how do I write? I write only the matrix concept of this. That's all. This is the only message to be taken, that circuit to be understood, and following the circuit principle, matrix representation of its operation should be understood, which can be programmed by the language of Python under the QIScript module. Next set up the quantum Fourier transformation. Classical to the classical things, we know that the classical Fourier transformation gives the time into frequency. Okay, so here also it does that the is a quantum implementation of the discrete Fourier transformation over the amplitudes of a wave function, and it is a part of many quantum algorithms, most notably that the Shor's factoring algorithm and quantum phase estimation. These two coupled together gives the quantum Fourier transformation. Simple mathematical expression is that a discrete Fourier transformation can be written into this form, which can be written in the quantum state like this. If I represent the quantum state into this form, I can represent that into this form. Okay, so that means in a classical case it remains same, but in the quantum case this is represented the quantum state and this is represented the quantum state. Okay, so therefore quantum state, if I introduce, I can write the quantum state transformation is nothing but that. So x, y, k, I represent the j, and this x I represent as this one. So therefore, I understand as a, this is my quantum Fourier transformation. So therefore, quantum Fourier transformation, if I do the unitary transformation, what happens? Under the unitary transformation, it gives me these two basis vectors entanglement with a summation sign. So we can say the quantum Fourier transformation transforms between two bases. One is the computational Z basis and the Fourier basis. And remaining things can be understood when we go further the quantum programming. Okay. Let us see an example. This is the 1 qubit AFT. I have represented as a quantum state, which is a superposition of these two basis states. And in case of the n equal to 2, x0 is called as alpha and x1 is called as a beta. So therefore, I can write by using the quantum Fourier transformation example as this form. If I explicitly write, I will get this. So y0, I have a 1 by root 2 of alpha plus beta. Y1, I can submit that the 1 where, and I will get the algebra as a 1 by root 2 of alpha minus beta. So therefore, under the unitary transformation of the quantum Fourier transformation of this psi, which is nothing but this, I can simply write into this form. So if I do the Hadamard gate on this, I will get the 1 by same kind of. So I can simply say that the unitary transformation of the quantum Fourier transformation on this psi is nothing but a Hadamard set. Okay. Same way I can just do the 2 qubit FT. It is little bit of algebra only. So you can finally get a 2 qubit a quantum Fourier transform matrix into this form. And finally, when you go for programming, you look at to know what is the matrix form so that you can design that circuit back. And that is why we have understood that the quantum gates are reversible. Okay. So this is a QFT circuit, which is a rotation matrix controlled RK gate can be designed by this. And when you have the 3, we can design that this S3. So therefore, quantum Fourier transformation circuit can be designed by doing this operation. There are the various modes of qubit circuit can be designed. U1, U2, U3 for all these things can be designed. Now coming back to the main topic of the HHL algorithm. Using this HHL, we can design or we can solve a linear equation AX is equal to B. when you do the classical operation, you see we are required to calculate x. X is nothing but the A inverse of B. So therefore, in quantum state, the x state will be nothing but the eigenvalue of the inverse operations multiplied by the vector state of the B. And that's why I mentioned that this module I have used. And before proceed further, let us sketch the how HHL algorithm fundamentals can be operated. Suppose that the matrix is given as a n by n Hermitian matrix. Okay, I am taking the root of the Hermitian matrix, but it can be non-Hermitian also. Later on, I realized that it can be non-Hermitian, and a very well quantum program can be designed by non-Hermitian matrix also. So B is my vector, so I wanted to satisfy this equation. Okay, so quantum B vector can be in the quantum formation can be written as a quantum state, which is nothing but my basis vectors a linear combination. Next step is to use the techniques of Hamiltonian simulation, which is nothing but my unitary transformation to the get state, which is e to the power IAT. And when you go for that, I will have this kind of eigenvalue structure, that is state of the system after this stage will be close to this operation. So therefore, I can write that finally that lambda j, which I require to calculate, which is nothing but the state solution, which would be nothing but the A inverse of B. So lambda j inverse is nothing but the ultimately A inverse B, because this is nothing but the A inverse of beta j uj would be equal to B, and lambda j will be equal to A inverse. So that means inverse matrix eigenvalue computation is essential, and which will be nothing but my x. So solution of a linear system by quantum algorithm HHL is nothing but to design the eigenvalue, and this eigenvalue is required to do the two operations, quantum phase estimation and quantum Fourier transformation. So I solved the simple classical diffusion equation. It is a 1D I have taken for the time being, but 2D, 3D can be designed. 1D reaction diffusion equation with an initial condition and boundary conditions. This is my boundary conditions. U of x0 t is nothing but sine of 2 pi is 0, and this is my boundary condition in another domain, with domain of the length is L equal to 1, and my initial condition is given by this form. Okay, so we apply this equation in the form of the system of linear equation. So what I did basically, this whole thing is designed as a finite difference method, and using that finite difference method, I will have an algebraical equation Ax is equal to B, and that x is equal to, as a solution state, we are trying to solve that. And for that, the discretization, if you look back to the previous one, for discretization, I have applied the Crank-Nicolson method. So we can say that the quantum Crank-Nicolson method, since I have coupled the quantum solver into this. So we require to find it out whether the matrix is singular or not. For that, we require to know that the condition number, and condition number is 1.6822 of that given matrix. So I understand that the matrix can be easily computed for its eigenvalues. So eigenvalues of the matrix is computed finally. And if you look at that, I will say you, this is a 4-qubit representation. So that means 2 to the power 4, 16 by 16 matrix you are handling. Okay, so this is my normalized classical state, and condition number is given again 1.68. For the classical state, Euclidean norm is given, and for the quantum state, naive Euclidean norm you get. And if you design the whole thing as a tridiagonal form by calling a function called tridiagonal tuplage, where only off diagonal and diagonal are required. So total computation time is taken 3.29 minutes. For the 16 by 16, if I go for the classical, it takes the just double 6 minutes. So it is understood that the speed of the computation will be exponentially faster. And this is the result you see. This is my approximation. This is the absolute error, and this is the relative error, and this is the exact solution. If you match to this thing in quantum computation, we have got this solution with a lesser time and with a different operation of the absolute error and relative error also we can be. This is the output of the heat conduction equation. Continuing into that, using the HHL algorithm, we plot that there is some 1D heat conduction again with a change of the different parameter, where my diffusion coefficient this time is the 0.1. And with this is the grid structure we followed. And we got the classical solution into this with an initial boundary condition. And if you go for the quantum, you'll get that for this R, which is a current number, 0.81, matrix A is given this, and is a diagonal from, see, you have a tri-diagonal, is a diagonal, this is an off diagonal, that is a super diagonal, and this sub diagonal. Similarly, here also matrix B you get. So ultimately A and B you have. So you take the inverse and multiply it, you'll get the solution into this. And this is a 3-qubit operation. That means your matrix is a 2 to the power 3, 8 by 8. Okay. Various kinds of circuits should be there. All the circuit representation will be reflected into this object. These are the classical solution, and the corresponding in the classically you have a solution, but in quantum mechanical you have a state. Every solution has got a represented as a state. So this is the outcome. You see initial boundary condition with the classical, and this is the initial boundary condition with the quantum form. And obviously there is no change, but speed is very high. So therefore we can understand that the quantum combination. And now this is the circuit which is designed by the quantum circuit of the heat equation. This is the circuit representation of that. As I mentioned that following the operation, you can design a circuit, and this circuit you require a quantum phase estimation, and then it is a representation of the diagonalization. So these two operations are required to design the circuit. This is my naive HHL solution state, and this is the tri-diagonal solution state. Okay, and this is the again another boundary problem, which is an interactive. You can feed it that your grid point, which is x varying from 0 to 1, and number of grid points have taken as a 6, and you have a left boundary condition as a 100-degree temperature, and 250 degrees centigrade is my right boundary condition. And if I go for the normal numerical values, I am getting this result. And quantum mechanical, I get the some kind of solution, and you see that my classical solution is this. That means initial 4 grid points I got the solution, and classical state quantum computation is giving this one. So therefore, if we go for your circuit, this is the special profile of the U, that is the temperature using the classical FDM, and this is the quantum FDM. So by this, I claim that a solver is designed for solving some engineering problem, which basically they do by classical method of finite difference. So I simply name it as a quantum finite difference solver. And continuing that, we can go for the quantum finite element solver, quantum finite volume. So all these finite element, finite difference, finite volume, all these numerical techniques, we can shift to the quantum computation by doing this HHL algorithm. So then next is the Deutsch algorithm. To some kind of function which can be done. We can just quickly go through that. What basically they do, this is a circuit representation of the Deutsch algorithm. So it is a control knot, you can say. Previously we have seen that. Now what basically does, then let us see that. If we start the state in a superposition of this, for n qubit, we have evaluated an exponential number of different values of the function. Now, how we can go for that? We can see that the Deutsch has given a proposition that this kind of concept can be literally break up into a very simple state. How we can do that? Let us see. What is the problem for the Deutsch solve? We have a function fx which will map into bits to bits. We have to determine if it is 1 to 1, that is f0 is not equal to f1. Classically, we need to evaluate basically both f0 and f1. But in quantum, let us see. Start with the 0, 1. Perform a Hadamard on both the qubits to give this operation. That you can easily see, we have explained. Apply the gate mapping of this xb into xb plus fx, okay, to give this output. Okay, now apply the Hadamard on this qubit 2 to get this one. Okay, then you start with the gate 0, 1, perform a Hadamard on both the qubits, as we have mentioned. Apply this one, we explained. Apply the Hadamard gate. We got this output. Apply the Hadamard gate on qubit 1. Up to this we have explained. Now we rearrange this outcome. Rearranging is then done by. If we rearrange and then go further, you will see that this part is nothing but the f0 equal to f1. Then you get this part, qubit 1 is in the state 0. If it is not, then qubit 1 is in the state 1. So automatically these two operations we will get. So therefore my Deuce algorithm circuit will be nothing but this. So a ket 0 and ket 1 is operating on both the Hadamard gate. You have this circuit X and Y. Here it is a Y will be moved into Y of exclusive of the fx. And if we go to the measure, we will get the H, and this is the measurement signal it is showing here. So therefore psi 0 and it will be 0 1, psi 1 will be then operation of this, and psi 1 will be operation of this. So therefore unitary transformation is saying that the Deuce algorithm is saying that a one-to-one mapping of this function can be done by this Deuce algorithm. Following that, many kind of operation we can do. Suppose fx equal to 0, fx equal to 1, fx equal to x, then I can write this one. Every operation can be transformed into that. I need only this matrix representation to design the program, and then finally you will get this kind. So Deuce algorithm basically generalize the behavior of the function in the operation. You can do many of the operation that we are not covering that. So Deuce problem was that you have a function you wanted to map one-to-one. That's all. Okay. So then his student Josa came into picture and then also changed into this algorithm in a better way. So if we need to evaluate 2 to the power n minus 1 plus 1 values of fx, how we can go for that? This is a circuit representation for that. And finally, we have an AND gate measurement. With the help of that, you will get the circuit of both this algorithm into this form. Okay. And when you operate that, you have the condition of the initial state, and then superposition can be written into this form. That was the basic output of that. Then finally you do the algebra, you will get that the psi 1, psi 2, psi 3. Psi 3 can be written into this form. And then finally you have the phase oracles. Phase oracles I am not explaining here because there are many other things, but idea is that the unitary transformation, if I operate on these two entanglements, I will get this operation. And algebraically, if I go further, a phase will be changed. Okay. And phase is nothing but the minus 1 to the power fx. Okay. Then we can, the Deuce algorithm start with this. Function evaluation is this. Hadamard gives this, and probability of measuring is this. So this can be easily programmed by simple quantum programming concept. Then Deuce algorithm start with this concept. It evaluates the function, Hadamard gives, and then probability measuring. So both the algorithms you can write down a good program to get what is the probability of measuring this particular y in this state. Okay. So then lesson learned from the DJ algorithm is that we can encode any mathematical function as a unitary matrix, and this algorithm generalize the Deuce algorithm by implementing the starting function. Okay. So this is the final circuit you require to program or you require to design. That is the basic job of the two Hadamard gate. Pass on to this, you'll get that measurement that I've explained also. This is the Deuce algorithm, and then finally you get this psi 0 and you get this operation. So computationally you have to design into this way. Okay. So this way you can go for the circuit. I'm not explaining because already I explained into the other form. The Deuce algorithm and algorithm, if I continue, there is a book by K. Chakraborty and J.P. Hayes. You can study the book for doing this programming part of this. Then comes back to the Shor's algorithm. It is a basically factoring algorithm. Algorithm is significant because it implies that the RSA, one number a popular public key cryptography method. Since I am not focused to the cryptography, so Shor's algorithm is possible, and it can track the RSA in polynomial time. It is a factoring basically. So it is designed by 1994 by Peter Shor and credited to G.L. Miller 7 years later in 2001. It was demonstrated by a group at IBM which factors 15 into 3 and 5 using a quantum computer with 7 qubits. So this is the challenge that how we can factorize a large prime number in the form of how many qubits. At present, QISKIT module can take up away 16 qubits, not more than. So 16 qubits means 2 to the power 16. You can say 16-bit computer and 16 qubit quantum computer. That's the reason. So algorithm is dependent on modular arithmetic, quantum parallelism, and quantum Fourier transformation. These three, if we can program, you will get the Shor's algorithm in your computer. This is the short gist of this, fa is equal to x to the power a mod n. If n equal to 15 and x equal to 17, you will get this design one by one. So if you write a program, how to factor an odd integer, then you can choose an integer q such that it will be done into this. Let us pick 256, choose a random integer x so that its greatest common divisor will be 1. Let's pick 7, and then finally you follow the procedure. You create the two quantum registers which are entangled. Input register must contain enough qubits to represent numbers as large as q1 up to 1 up to 255. So we need 8 qubits. Output register must contain the enough qubits to represent numbers as large as n on up to 14. So we need 4 qubits, and then finally we represent into this form. So we'll get your operation. So input registers are nothing but they store the information, and then you give the output register value. So factorize can be easily done. And then finally you'll get the collapse into these two factors. And then you can further go further the equal superposition to get all the factors of that. That's the entanglement. So we have successfully factored that 15 factorial. How to do that? So finally, you have by using the HHL algorithm, we can go for the quantum walk in the communication purpose. In the communication, there are two types of quantum walk. One is the discrete time, another is continuous time. And there is one Voronoi based that is being researched out so far, not been tested, but it is possible to design the sampling based quantum walk. Okay, so we'll explain that the one of these two. So this is the idea that classically we have taken that the sigma square is proportional to the time, but in the case of the quantum walk, sigma square, which is the variance, is approximately equal to time square. So we can say that the standard deviation grows at a quadratically faster rate in case of the quantum walk thing. And here we have applied the HHL algorithm, which is again quantum finite difference solver. So mathematical structure is into this walker and a coin. You have a time evolution state, this one. We can transform by unitary transformation by using psi t1. So we get that. Second model is that the continuous quantum walk consists of a walker and evolution, which is the Hamiltonian. And then with the help of the operator, a system can be applied with no time restriction. And we can say that the evolution via Schrodinger equation is nothing but the short introduction is the types, discrete quantum walk plus continuous quantum. Algorithms should be obviously element distinctness and continuous formula evaluation. So here HHL algorithm plays, everything will be converted into a linear equation. That means Schrodinger equation is converting to linear equation and then applying HHL algorithm. So when you go for this kind of thing, not going in the coin operator, shift operator, initial coins, all these things we are designed for the quantum walks. Okay. And when you go for that, we are trying to find it out that how the communication can be taken place. In Hadamard work, we get a symmetric probability. For a biased initial coin, we get a final probability distribution, which will be asymmetric. For classical, we should remember that is the dynamical behavior of a classical particle. So when you go for that, you have this operation. See, this is the classical operation, quantum operation we take, and the probability of finding the quantum walker at a position x at time can be done. So this is the probability we have. So total wave function can be considered as a coin is nothing but this one, where the total state of the quantum walk resides in this entanglement of these two. So initial position can be find it out by initial position and the coin operator. So discrete part, what you'll do, I will show that the output is the same coin operator you are writing, Hadamard gate, conditional shift operator you are writing, and when you are programming this together by using this transformation, so we can get this operation as a measurement on the coin and measurement of your P. Okay, P is nothing but the performance. So therefore, these two approaches, when you transform by the Fourier transform to get a closed form of the coin amplitude, you will see that a combination you will get that. So this is my Hadamard word. Okay, so that means a communication system can be designed by this way. So if you start the signal from here at a different position, I can get, and in the Hadamard work in the other position you get. In a classical work, it is a Gaussian distribution But in case of the quantum work, it is a double Gaussian distribution. So that means two kinds of communication you can have. That's the beauty of that, and it can be done by the HHL algorithm. So finally, we are concluding into that we have to have a quantum algorithm which should be designed by quantum circuits. And to know that the quantum circuits, we require to know that the quantum gate. And when you reach the quantum algorithm can be applied for some physical problem to solve that. And this is the journey of quantum computation and our transformation from classical computation to quantum computation. Thank you very much, sir.
Well, it has been a real pleasure, Professor Datta, to listen to your lovely talk. I would like to thank the people who are listening and the people who will be listening to your talk and watching it. Thank you very much indeed. And please, my greeting to your family and your beloved people.
Thank you, sir. Thank you,
And
sir.
don't forget that you have friends here.
Yes.
We all love you and take care of you.
Yeah. Yes.
Take care, my dear
Always.
friend, and really hope to see you sometime in India very, very soon.
Sure. So you should come there, and you were organizing some conference over here. You had
Yes,
given a message.
I'm planning to go there by sometime at the end of December this year.
Okay.
And well, I want to meet the people I love there.
Yes,
You
sure.
are one of those. And well, we're going to have a good time there talking about quantum computing.
Sure. Obviously, I'm waiting for that. Please do come. I'm really waiting for that. Eager to see you actually physically and discuss across the table rather than online.
We can have a cup of coffee and talk about quantum computing.
Yeah, sure. Definitely. Sure.
Well, I would like to thank my dear friend, Marco.
Yeah.
He's a very distinguished fellow here, a very good friend of many, many decades. And Galaxy A71. It was amazing. He said that, of course, it was an amazing talk. I don't know if Marco would like to ask something or say hello to this professor.
Yeah, sure.
Marco, you are mute.
Yeah.
Marco, you are mute. You are mute, Marco. There.
Yes. You need a quantum computer, and it's expensive. A quantum computer.
Yeah, quantum computer at present, sir, is there on the IBM. Okay, because you can run your program on the opening an account under the IBM computer, but it is really costly. But I think that all people around the world are researching toward how the cost can be reduced. Not only the cost, volume of the quantum computer should be reduced. At present, everywhere it is only the 2 to 3 story building, I can say. So therefore, we have to reduce the volume of the quantum computer and also its cost. I hope the people like Apple and the other vendors, they will be definitely coming back to the affordable quantum computer in near future. Of course, the time we have to start from now only. Thank you, sir.
Thank you.
Lovely. Well, once again, Prof, thank you very much indeed. And I'm going to see you very, very soon.
Yes, sir.
My dear friend Marco, do take care. My regard to your wife and family. And well, we're going to see each other very soon at the university.
Sure.
Bye-bye, my friend.
Yeah, bye.
Bye-bye, Professor. Thank you very much. Bye-bye.
Thank you, sir.
I'm going to send you the link. Bye.
Yeah, sure.
Bye. Bye-bye.
Bye.